I don't know if it's true. Okay. So maybe just some immediate, okay, I mean not immediate, maybe consequences of this basis theorem, which we prove that vector space, basis unique size. This is not unique but unique. We will try later count how many bases and all are there when we're working over finite fields. But right now, obviously, it's infinite. Immediate consequences of basis of vector space. So number one is that just take a m by n matrix. So you guys know what is row rank, right? So what is row rank? So row rank just be the dimension. Now dimension you understand, right? Just be the dimension of the vector space which is generated by the rows of A. Rows of A. You write the definition. So just see the definition. So you take the rows of A, right? And where are the rows of A living? You look at the rows of A. Where is this living? It is living in Rn. If the coefficient is in whatever Fn. Because every row is a vector in Rn, right? Then n columns. So you take the dimension of the rows. You can take the span and then you take the dimension. Take the vector space value. So this you understand. Okay. And similarly, you do for the columns, and that's called the column rank. Try to prove that they are equal. I already did it. But you see the column rank. So when you look at the columns, the columns they live in Rm, different vectors. And when you take their linear span and their dimension, right? This is row rank equal to column rank. Very, very useful. Okay. There can be other consequences, but we don't find all that. So this is the only one. Now let us try to do two things quickly. This is maybe some. Okay. So what we will try to show is again V be a vector space. Now we are not saying anything about finite dimensionality. Okay. Vector space. Okay. And let S be a generating set. Again, the definition of generating set remains the same. That given any for all V, right? V is equal to some finite sum. S may be infinite. We are in an infinite dimensional vector space. But the condition is, by definition, that every vector should be written as a finite sum. Okay. From S. Do you understand the definition? This will be useful when you do polynomials. So they are infinite dimensional.
Yes, sir.
So that's just the definition of generating set as it should be. You're not allowed to take infinite linear combinations, not here. In functional analysis, that comes as a natural thing, but not here. So S is a generating set. And again, I mean, same thing. Minimal generating set will be maximal. So S be minimal generating set, and hence it's also a maximal dependent set. It's the same, right? It's a minimal generating set, then it is generating, and so uh, if it's independent, it has to be maximal, because anything else you put in, anything else can be generated using these. So you put in anything else, it cannot be maximum independent again. So it's certainly maximal, and it is certainly independent, because if it is not independent, then it won't be minimal as a generator. So it's the same proof. So basically, when you prove that thing, when you go back and do this as homework, when you prove that thing, that maximal independent and minimal generating, you see that you did not use anything about dimension of the space. Not needed. If you have used, then you should correct your proof. That's not needed. It is just a pure symbol pushing argument. Because at every stage you're in every sentence you're only using finitely many vectors. There's nothing infinite about anything, any equation, any particular equation. So you have this, and then basically again we want to show that again you want to show this, but you see this time we are infinite. Okay. But the question, but before all this, the first question is, why does a maximal independent set exist? In finite dimensional vector space, it exists by definition, because the definition of finite dimensional vector space is that there is a finite generating set, and so any minimal generating set will also be finite, and therefore the maximal independent set will exist. That is definition. But in an infinite dimensional vector space, maximal independent set exists. Yes, it exists, and that is same as axiom of choice. Are you aware of axiom of choice? If not, you should read this from anywhere you want. Okay? As these things you have to read: axiom of choice, John's lemma, well ordering principle. One, maybe if you read a little bit, then one day we can discuss all those things. But they are not primary. So did I? Hundreds of books, but yeah, just find anywhere and read it. If you want a reference, but yeah, but it's not important. Naive set theory, almost, almost also the book on linear algebra, but it's fairly abstract. Anyways, naive set theory by Almos. But these statements you have to figure out what these things mean somehow. Yeah, I try to understand. So if needed here, then I'll tell you. For that, I will not prove that it is existing, that you assume. But now the interesting thing is some where we use the linear algebra and something from cardinality business classes we gave for homework. So we would want to see this. Right. So of course, you have that this is infinite. Right? Or maybe let's try to be more precise. So S prime is a generating set. One second. Okay? So you do one thing. So you assume, pay attention to this, assume that cardinality of S is infinite. Okay. If the cardinality of S is finite, then you go back to the previous problem. There you have already proved all this, right? If cardinality of S is finite, and then you want to prove cardinality of S prime is more, you have already proved that earlier. Okay. If cardinality of S prime is infinite, then it's already proved, and then there's nothing to prove. And if the cardinality of S prime is also finite, then you go back and see the previous proof. It's already done. That's easy. You already understood the proof. Don't if you cannot recall it immediately as a problem, but you have understood it. Not an issue. You can replicate. You can reproduce it gradually. Your own proofs. But now you assume that this is infinite. Then that's an interesting case. Okay. So if cardinality of S prime, if cardinality of S prime is less than cardinality of S, and you know what this means? This means that there is no surjection from S prime to S. There is no surjection from S prime to S. Cardinality of S prime is not more or equal to cardinality of S less. There is no surjection. S prime cannot surject onto S. So this is the assumption. Now we will try to get a contradiction. Its aim is to get a contradiction. Aim is to get a contradiction. Yeah, and I hope you have read Rudin's countable and uncounted chapter. That's important again, that you have to read. I mean, assuming you already know these things a little bit, but the point is that you should read it. So please read it. Please read that section. I think it's not a chapter. I don't remember. Chapter 1. So aim is to get a contradiction. And how do we do it? So yeah, let me see. So let us say that this prime is less. Yeah, and so what do you do? So if you let's try a different way this time. Okay. So if you write every element of, it's going to be simple actually. It's actually simpler than the finite case. We'll see. Yeah. So if you take S prime, some S prime in S prime, okay, right? Then this S prime is a finite sum, right? S prime is a finite sum. And forget the coefficients. Not much attention will be paid to the coefficients now. Okay. However, S prime only I'll write.
S prime is also a generating set, na?
Right. S prime is a generating set. Correct.
So the coefficients will be 0.
No. Why is the coefficient 0? No. Coefficient will not be 0. S prime can be generated using things from S. Coefficient will not be 0. Okay. So some SI. Right? Maybe.
Okay, you are writing on S. So.
Right. Yeah, in terms of S. Yeah. In terms of S, yeah, right. Okay. Something like this. These notations become really messy. So this is the situation. Okay. So everything from the generating set can be written as a linear combination of things from S. I am just doing it along with you.
When it's I to N summation of
some NJ.
Why we are writing?
It's just a linear combination, shorthand.
No, as cardinality of S is infinite, na? So
no,
and it's a generating set.
That's right. But at each stage, a generating set. And definition of generating set is that anything will be a linear combination of things from the generating set, but finite linear combination. Okay, linear combination will always be finite, whether you are infinite or finite dimensional vectors, and that is by definition.
Okay.
Right? That's what I said when I defined generating set, right? That the linear combination, the number of summands will be finite by definition. Obviously, that finite, how much is not set, that can change. 1, 2, 3, 4, but it will be finite. That's the catch. Okay. So each of this Sj prime can be finite. So, right. So in this way, if you collect if you take the union of these things over I, and then you take the union over J. So be careful with this. Okay? Maybe I will change this a little bit. This is where the infinite game comes. So you have S1J, S2J, maybe SNJJ. Okay? So for each thing from S prime, right? For each S prime from each thing from S prime, we have this linear combination, and therefore we have this set, this particular set you look before taking the union, which is involved in the linear combination. Okay, and this will happen for every J, where J is basically catching the things in S prime. Okay, so maybe there is just I can just write this as S prime J. For each S prime J in S prime, we have this. Okay, right? And this thing, you know that this thing is living in S, because I mean everything is coming from S. Okay.
What is the union supposed to mean?
So okay, so for example, you take this S prime J, and then you change the J, right? Okay, maybe I will stop using J. Sorry, I think it is confusing, right? There are other notations, but then I have to introduce those things. That is a little bit tricky, I think. But yeah, let me stop using the J, and let me just index it by S prime 1. For every S prime, we are doing this. Right? So to take S prime,
Explain the again.
sorry?
Explain the union again.
Yes, yeah. So what I'm saying is that so this union is indexed by elements from S prime, meaning that for everything in S prime, I have a set. What is that set? That set is that subset of capital S which was used in this linear combination to produce that S prime. Right? If you see it in the other way, then given every S prime in capital S prime, I will write it as linear combination of some things from S. So what are those things which I use? I am collecting for every S prime, and I'm taking the union over all S prime, over all elements S prime in S, capital S prime. Right? For example, if you take an example, a very simple example, you consider the polynomial right. You consider the polynomial 1 plus x dot till x to the power n, right? Then what do I have to use to get this? So this is, let's say, your S prime. So to get this, I will have to use 1 x to the power n, right? If you change the x prime to this, then what will my set become? N plus 1. Similarly, if you keep changing the polynomials here, you just take all possible polynomials. For everything, I will get something. Those things, those powers of x which I'm using, right? And they will come in this, and then I will take the limit. Obviously, there are repetitions, right? It's like a subset. Is this clear now?
So basically, we are taking those S from capital S, which are being used to make the S prime, small
Exactly,
S prime.
exactly. And S prime is
The
changing.
notation you used is just doing some.
Okay, sorry. I don't know what should I do. Okay, I can change the notation, but I don't want to do because it may confuse more. Okay. Okay. Sorry. Sorry about it. All right. So now it is fine, right? You try to write.
Yes, yes.
See if you can write some better notation, then better. Okay. All right. Certainly. So this is the thing. Now, what is the cardinality of this set? That is the question. And yeah, what is the cardinality of this set? Cardinality of this set is what? So the cardinality of this set is same as cardinality of S prime. Because S prime is infinite. Right? Correct or not?
Not getting strong.
Okay, yeah. So you can see this like this. So the cardinality of this thing is certainly less than. So what is happening? It's indexed by S prime, right? Indexed by S prime. So for everything in S prime, there is finitely many things, right? I mean, you assume that even if you take that there are countably infinitely many things, then the cardinality becomes less than the cardinality of this. Is this okay? Because for everything in S prime, you have an infinite tuple of A. You have a finite tuple. Finite, not even a tuple, less than that set, right? So for everything in S prime, you have a finite set. Change S prime, you have again a finite set, right? And you see that will be less than this, right?
Okay, yes.
Yeah, I mean, you can do a map, you can draw a map, right? So this S prime 1 comma S, you can map this to S prime comma 1. You can do all that, right? But not right. So this
Yes.
is it, right? But then, you go to Rudin or you go to last this whatever product. This is less than or equal. This is actually equal. Cardinality of any infinite set cross Cartesian product with countable, that the cardinality doesn't increase. So it doesn't change. It doesn't decrease, obviously. It doesn't change. Okay. Like countable union of countable is countable. This is like a generalization. So You can prove this is not different. And this is obviously contained in S, and what cardinality of S is S. Yeah. So if you assume this, yeah, if you assume this, then you get that cardinality of this is less than the cardinality. Okay. But this is a subset. So let me write this like this. Let's leave it like this. This is a subset. Okay. And this subset has less cardinality. So this is a subset. Okay. This is a subset of S, but it has less cardinality. What does that mean? If A is a subset of B and cardinality of A is less than cardinality of B, this is A. This is A. This is B.
Then A is a proper subset of B.
Exactly. That's all we need. Correct. Proper subset, right? So it means that there is something in B which is not in A. Right? So it means that something in B was not used. Something in S was not used at all in this generating set, while to make all these generating sets, right? So this implies that there is a S naught in S. That's which you are saying proper subset, right? Which was not used. Nice, right? Now it's fun. But this sounds wrong, right? Already it sounds like a contradiction, doesn't it? Right? So, I mean, there is some S naught which was like a part of a basis. Minimal generating set is like a basis, right? Which was not used. So how can you get that this S prime will be a generating set? Correct? I mean, how can S prime generate everything? Can S prime generate S naught? It should not, right? And but by definition it does. But by definition, this S naught is also generated by these S primes. Correct or not, right? Because S prime is a generating set, now we are using it at the end of the day. Okay. Something. This is wrong. Cannot happen. So how do you show it properly? Well, you have to go back, right? You have to write this S1 prime again in terms of S.
You said it's an infinite set. So maybe some elements are not in use. Generating set means that we will use the elements and we'll make the another element. But it's not necessary to use all the elements
If you don't use all the elements
in one time.
No, exactly. Not in one time, but overall also you are not using. That's the point. In the union, after taking the union also you are not using. You see the point, right?
Okay.
And that sounds like a pure problem. Certainly a problem, right? And that you will see here. I'm not asking you to complete this because it's a bit confusing maybe. It's a bit long, but I just write it right now. But of course, you see when you write this S1 prime, same business, right? Whatever, right? I write this, so, right? Then what do you get? You get on this side, you have a linear combination which is equal to S naught, but now it's purely in S. Purely in S. Right? Forget the middle equation. Everything is purely in S. And what does that give us? That gives us that these things in S are linearly dependent. Correct? This Sk is again summation of K, and S prime K is again some summation, right? So these are all linear combination is in S and it is equal to something in S, which is the contradiction because minimal generating set means it's an independent set. That's a contradiction. These things have to be done by contradiction. Okay. Is it good?
Yes, sir.
Yeah. So you see, this is the kind, and actually, you see, the proof actually here is easy, but It's just that the definition is a bit this thing, and this is a very useful when you do rings and so on, ideals and finitely generated ideals. These arguments in set theory, just like infinite combinatorics, something more than that. Okay. So there we have proved this. Let me also, this is just for fun maybe, I mean, little bit, if you want, 5 minutes. I want to talk about a little bit matroids. So there is something called matroids that generalize the notion of vector space in a different direction. And from there you can get an alternative proof. You can get an alternative proof that without using any matrices or anything, that vector space has the same. So let me just say what. Okay. So this is this notion of matroid. Very useful. This unify graph theory, this and that, similar using one language. Yeah. So what is this matroid? So matroid will be basically starting with a set. So you start with the set S, okay, and then you have F, which is just a subset of the power set. Okay, F is just a subset of the power set, family of subsets, power set. All right. So this is there, right? And yeah, only this section. And what you can compare this with is you can take your S to be your vector space and F to be those subsets of the vector space which are linearly independent. Okay, so let me call this I. This is very important when you do topology. Topology is also like this. Right? It's a set with a family of subsets. And measure theory. It's all about this second order options. Anyway, let's go quickly. So this is a situation, right? I think of I as a collection of independent sets. Okay, and now they have to satisfy some axiom. Satisfy some axioms, which is which is I think you told me very first day that if I1 and I2 is an I can write that not now. If I1 is an I and I is a subset of I1, then that is also in I. It should be like this, right? Subset of independent set should be independent, so you put it in our axiom. That this I should satisfy, family should satisfy this property. Subset should be there. And it obviously is satisfied by this. That's our model, you could say. If you're coming from linear algebra, if you're coming from graph theory, then I can be collection of all forests, maybe, if you know graph theory. There are other ways to see independent sets, some computer science, but yeah, this is just like this. And then I think the key axiom is that if you have I1 and you have I2, okay? So
What does it mean I belongs to I in the first?
I is a subset of I1.
Okay.
So it not belongs to subset. Right? Any subset of
and that implies
that this I is also in the independent set, independent system. This is in this family I.
I is a power subset of the power set of S,
yeah,
and
yeah.
S, what is S?
S is a set.
Okay, any subset of B.
Yeah. Yeah, any collection of subsets which satisfy these properties. Okay, and now we are taking that if B is in I2, okay, then there exists a in I1 such that given B in I2, given this is given first, then there is a such that you can chip that in, you can put this in and take this out, and this is also independent. Let me just check that. I hope it is correct. Metro had come from the other sources also, distributive lattice and so on. Yeah, they always write it like this. I don't know why. Okay, man. So you just don't take this. This still work in examples I have in mind, but they are not saying like that. I might be wrong. So if size of I2 is bigger than size of I1, that implies there exists uh, yeah, obviously there exists. It implies that there exists a in I1, sorry, in I2, such that you can still keep this independent. Yeah, this is certainly correct. This is also correct, right? So this is, you understand, right? I mean, if you have a basis, if this is the base, if this is the generating set, and this is this is an independent set, and if this cardinality is less, then you can put something in this which is still independent, right? Yeah. So basically, maybe I will talk about it sometime later. But from here, you can prove that all maximal elements in I have the same sign, and that is same as in this case it reduces to this. Yeah, this is probably abstract, but yeah, let me. Yeah. So in this way, you can prove that all trees have same number of cycles. Okay. But yeah, maybe we leave this. But just to show you, this is there. You can read it. Proof is very simple. But anyways, I will talk about it later. Okay. So let's meet at the time which we have decided. I don't know.
Sir,
Whatever.
and that is Friday, right, sir?
ये Friday था या Thursday था?
No. It's Thursday 8:30. Same
Thursday,
time.
Okay.
Thursday 8:30 or 10? 8:30, right? Correct. Yeah.
8:30.
So Tuesday is 10.
Oh, perfect. Nice. Okay. So we'll meet. Okay. Try to maybe
Yes.
Aryan can present a proof of this using method.
Yes.
Okay. All
Yes,
right then.
sir. I'll see.
All right. Bye.